Okay, welcome to the integration video. This is probably one area that at A-level a lot of students find the most difficult, and it's one of the biggest parts of the A-level. This video will be pretty long, but if you get through it all and pay attention, hopefully what you should find is that integration is nowhere near as scary as you may have thought, and it should make the questions seem a lot more approachable. So the first thing I want to talk about with integration is that there are two different aspects to it. And that's why it's considered very difficult by a lot of people, because most things in A-level maths have one aspect, e.g. you learn how to do it, and then you just repeat, and that's it. Whereas integration has two different parts. The first part is learning the tools in this toolbox and learning how to use them. And that's actually quite easy. That's not something that most people struggle with too much, with a couple of exceptions. But unfortunately, that's where most people's journey with integration ends, and most teachers then move on. But that's actually the easy bit done, and it's left out the hardest bit of integration, which is knowing which tool to use and when. When you see any random integration question, you may well know how to apply any one of these 5 different methods to solve integration questions, but how do you know which tool to use? And so that's going to be something that this guide focuses on quite a lot, because that's often the difficulty that really trips up students. So before we move on to sort of how, the more advanced forms of integration, obviously you need to know the standard integrals. Now, just know that integration is, by definition, the reverse of differentiation. So if you know the differentiations for tan x, for example, you know that that goes to sec squared x when we differentiate it, then obviously integrating will go the other way around. And so the same thing can be said for these other standard sort of differentials. And so the first thing you need to know for integration is just be able to recognize the standard results of integration. So for example, if you have x to the n where n does not equal -1, then this integrates to x to the n plus 1 over n plus 1. But if you have x to the n where n does equal -1, then that integrates into ln x. Similarly, sine x, because it's the reverse of differentiation, will integrate into minus cos x into sine x, etc., etc. The standard results are in your formula book. So for example, a to the x as the reverse of differentiation will be a to the x over ln a. And so just make sure you look at your formula book and you're aware of all these standard integrals. Now, the first method to do more difficult integrals is called the reverse chain rule. And this one you need to pay a lot of attention to. It is not used nearly enough, and it is usually the one that people have the most trouble with. So the first thing to know is, when should you try and use reverse chain rule? Well, the answer is, if in doubt on an integration question, always try and use the reverse chain rule first to solve the problem. This is because it's often the only way to solve certain questions, and most importantly, it's easily checked and ruled out, but it's also easy to miss. It's not always obvious unless you're actively looking for it. And so if you get in the habit of checking the reverse chain rule first on every single question you're not sure on how to solve, then if you can do it with that, great, you're done. And if you can't, then you can confidently choose one of the other tools, and those should solve the question. So a clue for when reverse chain rule is likely to be the method. The first one is if the integral looks extremely complex, and we'll see a lot of examples in this video. But for example, if I give you this integral, sine x cos x e to the sine squared x, well, dx, that should look just like a terrifying integral. And just remember that no questions in A-level will be super difficult if you use the right method. And therefore, if you have an integral like that, then the odds are there must be a trick, and that trick is reverse chain rule. So that's your first clue. The other clue to look for is reverse chain rule is used whenever you've got two functions as either a product or a quotient. We'll talk about that in a bit more detail. in a second. But so either sort of, f of x, g of x, or f of x over g of x, where one looks like the differential of the other. That's a good place to start for reverse chain rule. Now that's easier said than done. It's often very hard to spot when one's a differential of the other, but that's just the sort of crux of how the reverse chain rule works. So for example, if you take that nasty looking integral above, you should notice there's two functions, well, arguably two sort of functions. You could say that there's sine x cos x, and there's this guy, e to sine x sine squared x. And then you just sort of have to ask yourself, well, is one of them the differential of the other? And then you can sort of think, well, sine squared x, if I try differentiating that, that goes into 2 sine x cos x. And so that begins to look like it might be a good idea to start using reverse chain rule. So that's the basic idea of when to use it, but it's actually very hard to spot in some questions. So we'll talk about ways of making that easier now. But just quickly, when do you know not to use it? Well, first of all, just try and use it in lots of questions if you're not sure. And if you really can't get it to work, then it just won't work. But the example of where it won't be useful is where you've got two completely different kinds of functions, because then one function won't be the differential of the other. So for example, sine x e to the x squared. Well, those are two completely different functions, and they won't be sort of linked via differentiation. Ln x over sine x. Again, not going to be very linked. So sometimes you can sort of see that it's not reverse chain rule, but just don't trust your instincts here. As in, we'll go through how to spot it and check for it now. So you'll see in a lot of the examples we do that it's, even though it doesn't look like it immediately, that you can sort of get these hidden relationships. Sort of like this question. It's not immediately obvious that sine x cos x and e to the sine squared x are linked, but you can see the difference between something like this and something like this, where I can confidently say that sine x and e to the x squared, there's just no similarity there. Whereas sine x cos x and sine squared x, that's appearing in the e, there's some link there, so it's worth sort of thinking about it. Okay, so how does the reverse chain rule work? You'll probably know this, but effectively, it's where you've got a differential of a function and another function enveloping the integral of that differentiated function. So this is what most people see when they're taught the reverse chain rule. And personally, I think that this is one of the most confusing ways of explaining it. So we're going to move on from that very quickly. But before we completely abandon that, we're just going to mention the different forms of reverse chain rule to check for. And these will be power. So we'll have some differentiated function and then the function in a power. We'll have exponential, some differentiated function, and then the function itself inside an exponential, and we'll have trig, some differentiated function, and then something like sine of the function itself. Okay, so there's three types to keep an eye out for, and identifying which type you're using is actually something to pay a lot of attention to, because they can get confusing and a bit mixed up, and students often do that. So this is the method I would recommend you write all integrals in terms of before moving on and trying other methods. So let's say we have an integral like this. Let's just say sine x over cos squared x. I recommend you always get rid of quotients when you're looking for the reverse chain rule, and write any powers, especially when you've got trig, on the outside. So this, before I do anything else, I'm going to rewrite this as just sine x cos x to the minus 2. Okay? this would be rewritten as x plus 3, x squared plus 6x plus 5 to the minus a half. Okay, so especially this part with trig functions, but just whenever you've got any sort of quotient, any kind of power like that, just make sure you make it very clear, get rid of the quotient and just write it in this way. And this is because it makes it much, much easier to spot when you have something in the power form, which is the most common type of reverse chain rule. So, you know, just to make sure you really hammer this point home, if I have something like this, before I do anything else, I just want to write this as e to the x plus 2, e to the x plus 2x plus 5 to the minus 3 over 2. Okay? And this will make using the reverse chain rule much easier. So make sure you do that. Okay. Now, how does the reverse chain rule actually work? Well, if you can spot it by writing it in either the power form, the exponential form, or the trig form, what I recommend is you make sure that these things match perfectly. So for example, you have f dash is exactly the differential of f. Why is that so helpful? Well, once you've got it perfectly matching like that, the answer for power rule, reverse chain rule, is extremely simple. Power, the answer is f to the n plus 1 over n plus 1. Exponential is just going to be e to the f, and trig is just going to be sort of the integrated version of that trig function. So sine integrates into minus cos. So for example, it would be minus cos f. Okay, and so let's now just start going through all the examples you start to see. And included in these will be the important trigonometric identities that you want to sort of be aware of for integration. So one of the first ones you see is, let's say we get sine squared x. How do we integrate that? Well, you can't actually integrate sine squared easily, but what we do know is that cos 2x is 1 minus 2 sine squared x. And so whenever you see a sine squared or a cos squared, you just want to rewrite it in terms of cos 2x. So that will be 1 plus cos, 1 minus cos 2x, sorry, over 2. And so that is then the integral of 1 minus cos 2x over 2, which we can now integrate nice and easily in the following way. So even this kind of thing, which you can learn as a standard result, but it's actually technically it's a very simple application of the reverse chain rule. So let's start off with that. So this will be integral 1 over 2, which we can do, minus, well, what's the differential of cos 2x? Or what's the differential of the inside there? It's 2x. So the differential of 2x is 2. So we want to have, we could write this as a quarter of 2 cos 2x. Yes. And now that is just going to integrate into x over 2 minus a quarter of, and now we've got that exactly in the right form. And so we just integrate cos, which becomes sine. So it's quarter of sine 2x. Okay. How do we integrate sine x cos x? Well, you could write that in terms of sine 2x, but actually this is also an example of the reverse chain rule, because what could we rewrite this as? Well, we could say that this is simply cos x sine x to the 1. And so that, if you integrate it, we've got exactly the right differential of this function out here as cos x. And so this is just going to be sine x to the 2 over 2. So even though there's trig functions in there, it's actually an example of the power rule of reverse chain rule. So the power rule is the most important one that you'll see over and over again. And I know this is probably confusing at the moment, so just stick with this and you'll see a lot of examples now. So polynomials. If you are asked to integrate x plus 3 over x squared plus 6x plus 5 to the half. Well, first thing we want to do is rewrite it in the form we talked about earlier. So that's going to be x squared plus 6x plus 5 to the minus half. Now, if we look at this, this is our f, and if we differentiate that, we get 2x plus 6. So we need a 2x plus 6 on the outside. And so we can make that match exactly by taking a factor of a half out and rewriting. So instead of x plus 3, we've now got 2x plus 6. Think about it, a half times 2x plus 6 is just x plus 3. We haven't really done much, we just manipulated a bit. And the reason you want to be so careful with this and do it that way is because it means that you won't get these factors wrong. And so now that's in that form, we've done that into exactly the right form for the reverse chain rule. And so the answer is just whatever is in here, using the power rule, it becomes just that thing. Still got this half on the outside, and we add 1 to the power, so that becomes a half, and divide by the new power. So that's divided by a half. In other words, that cancels, and so the answer is just x squared plus 6x plus 5. Obviously, plus c in general. I'm not going to include those in this video just because it's a bit of a waste of time if I'm constantly writing plus c. What about if I made a small change to this, and instead of doing it to the half, I just got rid of that? Well, we can rewrite it in this form in exactly the same way, but now it's going to be minus 1. And that small change will actually have quite a big impact because it's still reverse chain rule and it's still a power form, but now this is to the minus 1. But when you integrate a power to the minus 1, you don't just add 1 to the power because that would be to the 0. So now this becomes half. And when you integrate to the minus 1, that becomes ln. So half ln x squared plus 6x plus 5. And you can see why I recommend writing it explicitly in these forms, because it makes it very easy to spot what the new power will be, or whether it will be the power rule, or whether it will become ln, etc. Horrific looking integrals. Well, I've written a few of them earlier, so let's take a look at them. So this thing, well, that looks awful to me. And so that suggests to me that the examiner is expecting you to spot reverse chain rule. So we've written it in this form. The only possible choice for f is this. So let's just check what the differential of that is. Well, that's, so f dash is equal to e to the x plus 2. Oh, look, we've already got it in exactly the right form. And so this is just an example of the power rule. So this integrates to become e to the x plus 2x plus 5 to the minus a half over minus a half. Now, what you might find is that it can be confusing to distinguish between when you're using the power rule, when you're using the exponential rule, and when you're using the trig rule. All I'm going to say is that if you've got a power at the edge to the n, then you are always using the power version of it. When you're only using the exponential and the trig form when there's no sort of to the n to deal with. So exponential form, you can have exponents and trig inside your power form, and you're still using the power version. So let's have a look at some exponential form examples. So if I ask you to integrate x squared e to the x cubed dx, well, that looks awful to me. So that suggests we should be using reverse chain rule. For the exponential form, we've not got any sort of powers on the outside of our functions here, so we've not got any like 3 there. And so this looks to me like if this is our f, then f dash is going to be 3x squared. So to make that match perfectly, we put a 1/3 there and a 3 here. And so now that matches exactly. And using the power, the exponential form, what's the integral of the exponential? Well, it's just itself, so it's the x cubed. And that's it, that's the answer. But we've got this 1/3 as well. What about the trig form? So if I want to integrate, let's make it a bit more confusing. 1/x sine ln x. Well, looks horrific, so it should make you think reverse chain rule. What could be our function inside? So this could be our f. What's f dash? Well, f dash is 1/x. So this is in exactly the right form already. And so all we do is integrate the sine, which becomes a minus cos, and copy it inside, so ln x. There'll be more examples of this later on, but hopefully this is starting to make some sense. What about integral sine x over root cos x? For that, we want to rewrite, before we do anything else, sine x cos x to the minus 1/2. And here we can see, this must be a power version. So differential of cos x, that's minus signs. We want to make that match perfectly. So if we put a minus out here and a minus out there, then that's the power form exactly correctly. So this will just be using the power form, cos x to the 1/2 over 1/2, or in other words, 2 cos x to the 1/2. What about integrating tan x? Well, you can't actually do anything with that because that's not a standard integral. So let's rewrite it as sine x over cos x, or in the form we want to write it in, sine x cos x to minus 1. Okay, so very similar to before. The differential of cos is minus sine, so we want to make it match exactly. And now it's matching, we can use the power rule to say that, well, we're integrating a power to the minus 1, so that becomes ln cos x. And we have a minus sign outside that we need to keep. Okay. And I lost that minus sign from earlier, so I just want to put that back in there. So you can see how reverse chain rule sort of comes up a lot. And I have more examples here. So before moving on to the examples, I just want to bring up a couple of traps that they often ask. X e to the x squared, we've already seen a similar version of that when I said x squared e to the x cubed. So make sure you're aware of the fact that you can't integrate e to the x squared. So if you see an e to the x squared, you need to use reverse chain rule to do it. What about sec-tan composites? So integral, this is very common and found to be very annoying by a lot of people. Sec squared x tan cubed x. Yes. Well, the first thing we want to do with trig is rewrite it as showing the actual powers that are involved. So sec x squared and tan x cubed. This just makes it much more obvious what we're dealing with. And then if we have a look at this, well, the more you know the differentials, the easier integration becomes, because the standard result here is that tan differentiates into sec squared x, or sec x squared. And so actually what have we got? We've got, if tan x is our f, then we've already got the differential just outside the function. And so this will just integrate straight away into tan x to the 4 over 4. And so you see this is very, very powerful and important for solving integral problems. What about 1 over x ln x? Okay, well, that doesn't look like the form we like to write them in. So let's write it as integral x to the minus 1 ln x to the minus 1. And then just looking at that, well, what does ln differentiate into? That differentiates into x to the minus 1. And so actually, that's already in the form we wanted in. So it's a power version with a minus 1. So what's this going to be? It's going to be ln of ln x. Okay, and so now let's sort of take a look at some examples. You should be able to do them yourself now, but So feel free to pause the video and see if you can do them. I'll just speed through them here. These are all going to be reverse chain rule. We'll do sort of a mixed set of examples near the end, because obviously that's the difficult bit with integration. So you can see immediately that this is the differential of this. It's already exactly perfect. So sine integrates into, it's the trig version. So sine integrates into minus cos. So we've got minus cos x squared plus x plus 1. Very close to correct. The differential of this is 2x plus 2. So we want to make this match perfectly by saying that this is half of the integral 2x plus 2. Then the cos function. That will integrate into half, because we've got that half outside. Cos integrates into sine, so sine x squared plus 2x plus 1. This one, well, that doesn't look like the form we want, so let's write it as x to the minus 1, 1 plus ln x minus 3, and this differentiates into 1 over x, so we've got the perfect differential already, so we can just say, okay, well, it's very obviously the power form, so it becomes 1 plus ln x to the minus 2 over minus 2. This one, 4, well, integral of 4, fine, that's not a problem, minus cos x to the 4, notice how I'm writing it like that, sine x dx. Well, cos differentiates into minus sine, so I want to write this very carefully, just to make sure I don't get the minus sign wrong, as integral 4 plus cos x to the 4 times minus sine x, because then it's perfectly correct. And so it's just the power form. So the first one is just 4x, and the next bit is going to be cos x to the 5 over 5. Okay, this thing looks absolutely awful, so it must be reverse chain rule. Now, what is this? This is root, so it's 1 plus 2 tan x over cos squared x. Now, one thing to be aware of, this is why integration requires practice. 1 over cos squared x is sec squared x. So I'm going to rewrite it like this. And the only reason I knew to do this is because I'm comfortable with, and then that's the half. I'm very comfortable and used to integration differentiation. So I know that 1 over cos squared x is sec squared x. And the reason I've known to write it like that is because I'm already on the lookout for reverse chain rule. And I know that tan differentiates into sec squared x. So that's why I wanted to write it like that. Now the differential of this whole inside will be 2 sec squared x. So I want to write this as half times 2 sec squared x, so that it's exactly right. And then we've done the half bit, so we can say that it's half 1 plus 2 tan x to the 3 over 2 over 3 over 2. Okay. Cos x over root sine x, we've sort of done similar. 1 over x ln x, we've done similar. 1 over cos squared x tan to the 4x. Well, again, we know that this is why, again, like I keep saying, practice is important and knowing what differentials turn up. So I see that tan to the 4x and think, okay, I want a sec squared. So I'm going to write that as tan x to the minus 4. And then I've also got 1 over cos squared, which I want to write just as sec squared. And so now I've got exactly the right form. So this is just going to be tan x minus 3 over minus 3. Okay. And finally, integral, writing this in the correct form, sine 2x cubed cos 2x. Well, sine 2x differentiates into 2 cos 2x. So I want half of 2 cos 2x. Then it's exactly the right form. And this will be sine 2x to the 4 over 4. And I've also got a half out front. So you can see why I stress reverse chain rule so much. Hopefully this makes sense. These integrals you just aren't going to be able to do any other way, most of them. And you can see it's very quick to sort of check for it. But if you don't spot it, and it is hidden some of the time. Like, for example, I think that question 6, that's quite hidden, that it's reverse chain rule, and question 8. But if you don't actively think to look for it, Well, if you try and do any of these ones via substitution or by parts, you're probably going to have a bad time. Okay, substitution. When should you use it? Well, obviously, if you're explicitly told to, that's most A-level questions. But if they are nasty and they decide to give you an integral where you're supposed to use substitution, but they don't tell you the substitution, then it's actually quite simple. You want to use it if you have a function in the integral that will be simplified by a shift or one that looks like a trigonometric identity. So what do I mean by that? If I have this integral, let's do something like that. Well, actually, what's causing that to be a problem? Well, it's the x plus 4 on the bottom. That's the annoying thing. So this looks like it would be simpler if I just try replacing x plus 4 with u. So just try that simple substitution. And you might ask yourself, well, why didn't I try u equals root x plus 4? Well, the answer is simply u equals x plus 4 will be much easier to make the substitution. And so you don't usually want roots in your substitution, and they both would work. So x plus 4 is easier than root x plus 4, so why not use the easier one? What about this trigonometric identity one? I mean, so this, for example, well, what trigonometric identity does that look like? So that actually reminds me of sine x is equal to the square root of 1 minus cos x, cos squared x. And so if we tried u, or in this case, sorry, x equals sine theta or cos theta, either one would work, that suggests that this might be a good substitution to use, simply because if you think about subbing this in, then that would make the whole bottom part simplify, because the square root of 1 minus sine squared would be square root of cos squared, which is just cos. Similarly, if I have well, that looks a bit like a trigonometric identity, because 1 plus tan squared x squared. And so I could try x simply because that would simplify the bottom. So that's all you want to do for if you really do have to come up with substitution, which isn't very common in A-level. But that's actually all there is to it in terms of coming up with clever substitutions. It's just looking at what would be helpful. Now, how do you actually do integration by substitution? Well, once you have the right substitution, either you've been told or you've guessed, they're actually extremely simple because they're very algorithmic, and you just follow the following 4 steps every time, just explicitly. So let's do this one, and let's say we had a pair of limits. So we had between 0 and 1 with dx. So let's just walk through it. We're using x equals sine theta. Okay. What do we need to do first? We need to find dx. So what we need to do is we need to differentiate the substitution and get dx d theta equals cos theta. And so dx, which we're trying to get rid of, is just going to be cos theta d theta. Okay. Now, if we have limits, we need to sub those into the substitution to find the new limits. So the lower limit is when x equals 0. So we're saying 0 equals sine theta. What does that tell us theta is? Well, it tells us theta equals 0. That's our lower limit. The other one is when 1 equals sine theta. What does that tell us our upper limit is? Well, that's when theta equals, let's use radians, so pi by 2. And so our new limits are 0 and pi by 2. Now we're in this position where we can just replace all the x's with the new variable, including the limits. So we've got 0 to pi by 2. dx is now cos theta d theta. 1 over root 1 minus x squared is 1 minus sine squared theta. And now, if you've done everything right, it should just tidy up a lot, which is now going to be cos theta over, well, cos theta d theta, which is literally just integral of 1 between 0 and pi by 2 d theta, which is going to be theta evaluated between pi by 2 and 0, which gives us an answer of pi by 2. Now, And that's really all there is to it every time for substitution. We'll see more examples in a second, but that's just all you're going to be doing every time. And I've just done step 4. Just a quick note, if you don't have limits, you don't have to do the step 2, obviously, but you do need to replace it with the final step, step 5. So let's say we need to solve the integral of x over root x plus 4 and get our answer in terms of x. So what substitution do we think? Well, I'm thinking a shift will make it easier. So let's just try u equals x plus 4. So that means that du dx is going to be 1, or in other words, du just equals dx. Okay, great. And so integral, well, x is going to be u minus 4. So we've got u minus 4 over the square root of u du. Okay, why is that helpful? Well, actually, this is just the integral of u to the half minus 4 u to the minus half du. And that is just going to be u to the 3 over 2 over 3 over 2. So let's streamline this a bit. Over 3 over 2, so that's times 2 over 3, minus 4u to the half over a half, in other words, times by 2, so 8u to the half plus c. And so now, because we don't have limits and they want the answer in terms of x, we need to sub back in for x into our final answer. So this is equal to 2 over 3 x plus 4 to the 3 over 2 minus 8 x plus 4 to the half plus c. Okay, so let's have a look at some substitution examples. You should see that these are just exactly the same thing every time once you get used to them. So this first one, use substitution x equals tan theta to show this. So, okay, let's do as they say. So the first thing is x equals tan theta. We need to use this to get rid of dx. So dx d theta equals sec squared theta. So dx is sec squared theta d theta. Okay, then the limits. So the upper limit, we've got root 3 is our x value, and that equals tan theta. And the lower limit, 1 over root 3 equals tan theta. So the upper limit will be theta equals 60, or more accurately, in radians, it's going to be pi by 3. And the lower limit will be pi by 6. Okay, and so now, summing these in, we get pi by 3, pi by 6, 1 minus tan squared. I'm going to write tan theta as t squared. So 1 minus t squared over 1 plus t squared. Dx becomes sec squared theta, d theta. Okay. 1 plus tan squared is just sec squared theta. So this will simplify into just 1 minus tan squared theta, d theta. Now, tan squared, we don't know how to integrate, but sec squared we do. So let's replace tan squared with sec squared, and this becomes pi by 3, pi by 6, 1 minus tan squared is sec squared theta minus 1, so 1 minus sec squared minus 1. In other words, what we get is, I believe, just 1 minus sec squared minus 1, so we get 2 minus sec squared theta, d theta. And so that is going to be 2 theta minus tan theta, that's the integral of sec squared, between pi by 3 and pi by 6. And so the answer is just going to be 2 pi by 3, well, 2 pi by 3 minus pi by 2 pi by 6. So in other words, just, I believe that's just pi by 3. Minus, I believe that's root 3. So root 3, and then the other limit will be plus 1 over root 3. Okay, and so comparing that to the answer, let's pi by 3 to root 3, so that's Right, so just tidying it up a bit, this is equal to pi by 3 minus root 3 plus root 3 over 3, which in other words is 1 over 3 brackets pi minus 2 root 3. And that is the answer. So as you can see, substitution, very algorithmic, not too difficult. Use appropriate integration techniques to show that sine root x dx equals n, where n is a positive integer. Okay, so here they haven't given us a substitution, but just sort of thinking through, well, reverse chain rule clearly isn't going to work. As you'll see later, parts isn't going to work, and so substitution's really our only option. And so what substitution do we use? Well, just the obvious one, really. What's causing a problem? It's root x. So let's just say root x equals u. And hopefully this will work out. So in other words, or root x, we can write as x to the half. And so du dx is equal to x to the minus a half times a half. So half x to the minus a half. And we want to get what dx is. So that means dx is equal to 2 du x, x to the half. And x to the half is just u. So in other words, dx is just 2 du times u. Okay, root. So now we need to do the limits as well. So the lower limit, obviously u lower is just going to be 0, and u upper is going to be the square root of quarter pi squared, which is pi by 2. Okay, and so this integral becomes 0 to pi by 2 of sine u, and then dx is, we've got a 2, and we've also got a u du. Okay, now this, we then need to use integration by parts to solve, which we will be approaching in the next part of the video. So this is actually an easy integral to solve now, but we just need to learn something else before we can finish it. Finally, we've got use substitution, u equals sine x to find an expression for this, and you just need to do exactly the same thing. So what we need to do is we need to find out what how to get rid of sine x, how to get rid of cos x and tan x given sine x. So how do we do that? Well, we know that u is sine x. So what you can do for these is construct a little triangle where we say that, okay, if this is x and this is u and this is 1, then in this triangle, we know that sine x equals u. And so now just using this triangle, we can say that this side is root 1 minus u squared. And so immediately that gives us that cos x is root 1 minus u squared, and tan x is u over root 1 minus u squared. And so that allows us to just do the substitution. So u is sine x, so du dx equals cos x. So du is cos x dx. Okay, so in other words, dx is du over cos x, or du over root 1 minus u squared. Summing this all in, then we get cos x is root 1 minus u squared. So root 1 minus u squared plus tan x, which is plus u over root 1 minus u squared, all over 1 plus tan squared, which is going to be u squared over 1 minus u squared, times dx, well, dx is du over root 1 minus u squared. And now tidying this up a bit, if we multiply the top and bottom by 1 minus u, root 1 minus u squared, this becomes integral 1 minus u squared plus u all over 1 plus u squared over 1 minus u squared times 1 minus u squared. A bit annoying, this question, but still doable. And so that is going to hopefully simplify nicely into integral of 1 plus u minus u squared over 1 minus u squared plus u squared. So finally, we get to the idea that this is actually just 1 plus u minus u squared du. And so integrating that, there are no limits. So it's just u plus u squared over 2 minus u cubed over 3. And so when there are no limits, we need to get our answer in terms of x. So returning to what u is sine x. So this is equal to sine x plus sine squared x over 2 plus sine cubed x over 3. Okay, so that's enough for substitution, I think. Moving on, we've got integration by parts. So this is quite a useful trick to know. It's useful for two functions multiplied together where one function would be simplified by differentiating it. For example, x e to the x. Well, this is two functions multiplied together, and one of the functions, e.g. x, usually we're talking about an x, would be simplified by differentiating it. So that would be a good example of where it would be useful. Where else? What about x ln x? Well, there, actually, when you see a ln x, you want to differentiate the ln x, because while, yes, it's true that differentiating x simplifies it, actually differentiating ln x simplifies that by more, because that becomes 1 over x, which is much simpler than ln x. So that's helpful as well. Those are really the only cases that you'll see integration by parts used. So let's have a look at how it works. So it's very simple. If you have an integral of two products, u and v, then you can say via integration by parts that the integral of that can be rewritten as evaluated between the limits u integral of v, so integrate one of them, leave the other one alone, minus the integral of the first one differentiated and the other one, again, just integrated. And that's it. So this should become very simple once you see some examples. So let's take a look at, well, let's do a simple one first. So that x e to the x dx. Okay, well, which one is going to be useful to differentiate? Well, x. And so that means we integrate e to the x. And so this will be x left alone, e to the x integrated, which is e to the x, okay, minus the integral of x differentiated, which is 1, times the integral of e to the x, which is e to the x. And since we've done it without limits, we can get rid of those square brackets and just say this is x e to the x minus the integral of e to the x, which is just e to the x. So that's our answer. Very simple. Similarly, x sine x, x cos x, stuff like that will be similarly solved by this kind of thing. What about the integral of ln x? This is an important example because it's hard to know what to do if you haven't seen this trick. Well, this is actually solved by integration by parts. What you do is you say that the thing we're integrating is actually just 1, and the thing we're differentiating is ln x. And it's a little trick that it's very hard to know to do unless you've seen it before. So here we'll just get, if we do that, well, that's going to be integral of 1, so that's x ln x left alone, minus the integral of, well, ln x differentiated, that's 1 over x, times the integral of 1, which is x dx, which ends up being x ln x minus the integral of 1, which is just x. So that's a nice little trick to know. Similarly, for x ln x, whenever you see a ln x for integration by parts, you always want to differentiate the ln x. So this will be ln x left alone times x integrated, so x squared over 2, minus the integral of, well, x integrated, so x squared over 2, ln x differentiated, 1 over x, and so you can see how that's going to finish off. Again, quite an important example, e to the x sine x. Here, it doesn't matter which one you pick. I'm just going to pick e to the x to integrate and sine x to differentiate. And what you actually have to do for this is it's a nice little trick where you say, whatever this thing is the integral I. And we can also say that this is the same by doing integration by parts as e to the x sine x left alone minus the integral of e to the x integrated, sine x differentiated, so cos x. And if we repeat that again, we get, just leave this guy alone,
If we apply integration by parts to this, we can say that this is going to be, well, e to the x integrated, cos x left alone, minus the integral of e to the x integrated, cos x differentiated, so that becomes minus sine x, so this becomes plus e to the x sine x. And if you have a look at what that is, well, that is just the original integral we had. So what we end up doing is we get this little trick that says that, okay, the original integral I must be equal to e to the x sine x minus e to the x cos x minus itself. And so we end up with 2i equals e to the x sine x minus cos x. And so somehow that's told us what the integral is without actually really solving the integral in a way. So it's a neat little trick that you need to be aware of.
Okay, so the final sort of tool for the toolbox is partial fractions. These are very easy. You should already be aware of how to use partial fractions, and effectively, it's just exactly the same as standard partial fractions. So if you see an integral like this, let's say it's something like ax plus b over x squared plus cx plus d. Well, that is going to be pretty tricky to integrate in its current form, but you should know from partial fractions that this could be rewritten as sort of the integral of some number over x minus alpha, where these are the roots of the quadratic on the bottom. And then this form, obviously, it should be clear that this just integrates into ln, a ln x minus alpha, b ln x minus beta. And so that's just partial fractions. I'm not going to give any examples here because they'll come up later on, and it's relatively standard. So that's actually everything in terms of actual integration, all of the different tools you can come across. But now what we're going to do is we're going to go through a bunch of mixed examples. And this is very important because applying the tools one by one is not too difficult, but it's when you get these questions, which is much more like what you'll get in an exam setting, where you're not sure which tool to use. So try and give them a go yourself. But if I just go through them, what I'm going to do is I'm going to talk about my thinking process that gives me a clue on what to try. So if we just make a start here, the first thing I'm always going to think about every single time is, can I make reverse chain rule work? I've outlined why that is earlier, and it's going to be no different here. So for example, in this first question, I can immediately see, well, actually, just quickly, I could expand this out and just integrate it like standard, but actually reverse chain rule, you want to get so good at recognizing it that you just default to it, because if you do spot it and make it work, it's a very quick way of solving the question, and it solves a lot that won't be solvable otherwise. So here we can say that this is actually exactly the differential of this. This is to the 1 to the power of 1. So this we can immediately just write straight away, no working, that it's going to be x squared plus x plus 1 to the power of 2 over 2. What about this next one? Well, again, I think we've seen something almost identical to this earlier. Should be very clear because it looks awful. This is reverse chain rule. That's the first thing we're going to try. And it's the trig form, so that will just be cos integrating into sine. And we'll need a half out the front to make this exactly the correct form. And then this will be sine, or half sine squared plus 2x plus 1. Okay, next one. Well, the first thing, as I always say, is I'm going to try reverse chain rule. But here, you should sort of immediately notice that's not really going to work, because if we rewrite it in the form we want, that's 2 plus root x to the minus 1. And the differential of what's inside this bracket here is going to be sort of, 1 over root x. And we don't have anything like that outside. So actually here, reverse chain rule hasn't worked. And so then once I've ruled that out, I can pretty confidently say, well, what are my other choices? Well, partial fractions isn't going to be available. Parts doesn't look useful here at all because there's not even two functions to sort of There's not a function that obviously gets simple when I differentiate it or anything like that. So it must just be substitution. That's our only choice left. And what substitution do we use? Well, it doesn't look like a trigonometric identity to me or anything like that. So I can't be that clever. And just remember, obviously, when you get into a situation like this, it might feel like, you know, you're sort of stumbling around in the dark. But what we've actually done there is we've ruled out almost every other option. And so what substitution do we use? Well, don't try and be too clever. Just look at it and say, well, what's causing a problem? It's root x. So why don't we just try the obvious one and just say u equals root x and see where we get. So if we try this substitution, we get du equals, I believe, well, du dx is half over root x. So that will be 1 over 2u, just skipping some steps, dx. And so we get that dx is equal to 2u du. Okay, and so subbing that into the integral, we get 1 over 2 plus u times 2u du. Okay, and so that's going to be the integral of 2u over 2 plus u du. Okay, and that's actually still looking not perfect. So what do I want to do? Well, again, just looking at that, why don't we just do another substitution? Because here it looks like a shift will be helpful. And so I'll just say, okay, then v can be equal to 2 plus u. And that makes du just dv, just sort of think it through. And it's a very quick substitution. So we get u is v minus 2. So we get 2 v minus 2 over v dv. And that is going to be the integral of just, well, now we can say that's just 2 minus 4 v to the minus 1 dv. And so the answer is 2v minus 4 ln v. And so sort of working our way back, well, that means that we know that v is 2 plus u and u is root x. So we can say finally this is 2 of 2 plus u, which is 2 plus root x, minus 4 ln 2 plus root x. And that's our answer. So obviously slightly trickier than the rest, but hopefully you can see it's not like you're coming up with anything particularly clever. You're just ruling out the obvious paths, and then there's only one path left usually. So now if we take a look at 137, well, that looks to me like it's pretty nasty, but in its current form, I don't think reverse chain rule is really an option, because, you know, that's e to the x plus e to the minus x plus 2 to the minus 1. If you differentiate that, we need something outside, and there's just nothing there. So looking at that, just thinking about how that turns up in other questions, that looks to me like sort of a hidden quadratic. So why don't we try multiplying the top and the bottom by e to the x first of all? Because then that turns the bottom into e to the 2x plus 2 e to the x plus 1 dx. These are very hard questions, by the way, just so you're aware. So if you can get good enough to do these, you'll be definitely good enough to do the questions you might see in exams. And so now looking at that, well, that's a hidden quadratic. So I can write this as e to the x over e to the x plus 1 squared. Okay. And whenever we've got a quotient like this, I want to write it as e to the x plus 1 to the minus 2 dx. Okay, well now actually, now that we've written it in that form, have a look at the differential of this. That differentiates into e to the x. So all of a sudden, we've sort of stumbled upon the form for reverse chain rule. So this is just going to be e to the x plus 1 to the minus 1 over minus 1. And that's it. Okay. I think hopefully it should be, actually some of these next ones are a bit nasty, so let's do those as well. So if I just tidy this up a bit, I'll get rid of this. Bear with me for a second. Okay. So x squared tan x cubed plus 1. Well, that should seem horrible enough such that there's no other choice but reverse chain rule. Tan, if you think about tan, if you're not sure about it, tan is sine over cos. Just thinking about tan first, not for this integral. And cos differentiates into minus sine, so write this as this, which is rewritten as this. And so I always do write things like this just because it makes it a lot clearer. And that would just be minus ln cos x when we integrate it. And so applying a similar idea here, well, if we know that tan x integrates into minus ln cos x, and the differential of this thing is going to be 3x squared, so we want to make that perfect. So if we put a third outside, we get a 3 there. And actually, we've got exactly the differential outside, so we just need to integrate tan using the trig version of reverse chain rule. So this will just be minus ln, well, we've got a third, so we need that. So minus 1/3 ln x cubed plus 1. That'll be it. Okay, 139. Looks a bit like reverse chain rule, but unfortunately, x cubed is not going to be what we want for the differential. So I think what we're going to have to do is just think about this. We've ruled out reverse chain rule. Substitution doesn't look particularly helpful. And so I would say we've got parts here is what we want to try first. So if we just do parts, what do we want to differentiate? What do we want to integrate? Well, usually we want to differentiate the x, but in this case, we've got a ln. And for using parts, we almost always want to differentiate the ln. So if we just do this, we get that this is equal to x to the 4 over 4, the ln left alone, minus the integral of x to the 4 over 4 times the differential of that ln. So the fully inside that brackets is x squared plus 1. That's the most inside function. So that's going to be 2x when we differentiate it. Moving out, that's going to be the ln being differentiated to 2x squared plus 1. And so just sort of carrying on with this part, we get that's the integral of x to the 5 over, well, I'm going to call this half, x to the 5 over x squared plus 1. Okay, slightly tricky, clearly. That looks to me like I'm thinking a shift would make that easier, because this would be very easy if the bottom weren't x squared plus 1. And so just looking at that, I think a substitution of, let's just try the easiest one first. So that bottom is what's causing problems. So let's try u equals x squared plus 1. And so we get du, I'm missing a dx here. So du is equal to 2x dx. And so that integral becomes minus half integral, u x squared is u minus 1. So this is u minus 1 to the 5 over 2. Actually, let's just rewrite this top as x to the 4 times x dx, because we know that x dx is going to be du over 2. And so this is actually slightly nicer. It's u minus 1 squared times du over 2 all over u And hopefully you can see now that that will be easy to integrate because we just expand out the u minus 1 squared, divide through by u, and then it's very standard differentiation, integration. So very nasty question, but you can see how sort of we make progress through it just by doing what we can do at each stage. And then finally, sine squared x, sec squared x dx. Well, looks like one that's worth thinking about. That is, we could rewrite that as just, and I want to make it clear, I'm not sure what to do yet. And that's true on lots of difficult questions, but it doesn't mean you can't solve it. You just want to sort of keep an open mind and have a look at it and sort of get an idea for what could be the way to solve it. So that's sine squared x cos over cos squared x. Well, okay, so having rewritten it as sine squared x over cos squared x, that's obviously just the integral of tan squared x dx, which we can't integrate, but we can use a trigonometric identity to make that into 1 plus sec squared x dx, and this we can integrate. That's just x plus tan x, and that's it. So hopefully those examples sort of are helpful for illuminating sort of what you want to, what sort of process you want to follow. I'm not going to do the rest of these just because I think it would become overkill. I think it's worth you trying these for yourself, but what I will do is sort of talk through how you might go about doing these. So hopefully it's very clear, just immediately, I don't even need to think about it. This is going to be reverse chain rule. Why? Well, because it's just way too difficult to do any other way. And so it must be set up to be reverse chain rule. This one, that's actually just standard. Just as a quick point on how I do these kind of integrals to make sure I don't get the coefficients wrong once I've integrated, I like to just make it so that it's, well, you can take all the 4 over 3 out. And I also like to take a 2 out from the bottom. So this is 4 over 3 of 1 over 2x plus 1. So I would take a 2 out again from the bottom and say this is now the 4 over 3 times 2 of 1 over x plus a half. And the reason I like to do that is because now I don't have to worry about getting that coefficient on the side wrong. I can just see that that's 2/3 of ln x plus a half. So I won't get, basically I won't get this bit wrong, which is something people get wrong all the time. This one, well, looks to me like we've got a 1 over cos squared, and that's worth recognizing as sec squared. And we've got a tan, so it's going to be reverse chain rule. So 221 sine 2x over 1 plus cos x. So immediately what we need to do is get rid of that sine 2x. So that's going to be integral 2 sine x cos x over 1 plus cos x. And we can't use reverse chain rule on that because the differential of cos x is just minus sine, and we've got another cos x on top to deal with. Parts doesn't look helpful at all because, I mean, nothing there is going to become easier if we differentiate it. And so our only real choice is substitution. And so, again, we've ruled out the other options. And so substitution, well, which one do we use? Well, you don't have to be too clever. There's nothing particularly sort of special jumping out at me at what we want to use. So I'm just going to say that u equal cos x. In fact, actually, I'm going to say that u equal, and either one would probably work, but let's just say u equals 1 plus cos x, just because that will make the bottom as simple as possible. And so then we've got du is equal to minus sine x dx. Okay, and so that means that if we plug that in, we've got on the top 2, so cos x is u minus 1, so 2 of u minus 1
sine x dx is minus du. So we've got a minus du here. And on the bottom, we've just got u. And hopefully it's very clear that that's worked. We don't really need to do much more than that. If we sort of expand that out, it's just going to be simple integrals. Okay, sine cubed x, I think that's worth talking about. Nothing we can do with that. So before we do anything else, we just want to sort of mess around with it. Well, that can be rewritten as sine squared x times sine x. In other words, 1 minus cos squared x times sine x dx, which if we expand that out, that becomes sine x minus sine x cos x squared dx. Remember that way of writing things. And now that we can just integrate, because that becomes minus cos x. The differential of cos is minus sines. We've already got that exactly. And so it's plus cos x cubed over 3. Okay, I think you've probably got the point now. If you are feeling confident, hopefully it's worth you trying the rest of these. Again, just remember that in general, these can be tricky, so don't be disheartened if some of these you find difficult. They're on average much harder than the ones you'll see in the A level. But hopefully that's given you an idea to not just how to do integration, but also how to know which method to choose, because that's often the difficult bit that people find hard. So now we've really just got to sort of tidy up and finish off with the practical uses of integration and sort of a few little guides on how to sort of handle integration questions. So the first thing to mention that's just something to be careful of. An area, what's the difference between an area and an integral? Well, if I have a function like this, and they ask me for the integral between a and b of f of x dx, where this is, let's say this is a and this is b. Well, the integral of that is just, as you can see, you just literally just integrate the function between a and b. And whatever the answer is the answer. Whereas if they ask me for the area under the curve, then what I need to do is I need to take into account that what an integral will tell me is it takes into account positive and negative. So whereas area, I want everything to be positive. So a, when I do the integral a, if I call this c, that will be the integral between a and c of f of x, but that will turn out to be negative because it's below the curve. But you can't have negative areas. So what we want to do is take the modulus of this and add it on to the integral b, which is going to be from c to b of f of x dx, and that will be positive. But so just be aware of the difference between whether they ask you for an area or an integral and how to deal with it. In order to do this sort of accurately, you do need to sketch functions very carefully. And just also be aware that on a lot of differentiation questions, the difficult bit is integration questions. The difficult bit is not actually the integration itself. It's setting up what integration you need to do. So for example, if I have some sort of function that's like this, and then they've also given me a straight line that's like that, and they want to know this shaded area. Well, before I even worry about doing the integration, what you want to do is very carefully set up exactly what integrals will add up to that. And the way you want to do that is sort of break it down into little sections very clearly, and then just work out each one individually. So for example, I can see that this is 0. If this we say is A, and this point of intersection is B, then how do I get that shaded area? Well, it should be very clear that A, and they want the area, remember, A is going to be negative. So that's going to be the integral between 0 and A of f of x dx. And I'll just call this line f of x and this line g of x. So
that's going to be that, and that's going to be negative. So I'm immediately going to want to modulus it to make it positive. Okay, well, what else do I need? Well, I also need that area above the axis. And how am I going to get that? Well, that's the area below G, and it's from 0 to B. So if I sort of talk about doing that, but that's going to get me this whole thing, including this little bit that we don't really want. So let's talk about that in a second. And the way to do this and make it easy is just label things very carefully. Call that B, and this part C. That's not very easy to see, is it? Call that C. Then what do I want? Well, the total area is going to be, so it's going to be area wanted is going to be, just looking at it, well, it's going to be A plus B, but B, remember that B is that whole orange triangle. So we need to subtract off C. And then all we need to say is that, okay, well, what is B? B is the integral from 0 to B of G of X. And C, well, that's the area under the curve F of X from A to B. And once you've set everything up in that way, now you can just confidently go through and get all the marks of the problem. But you can see that clearly this part was actually the most important part in terms of getting the question right. And people really don't pay this enough attention or care. And so just when you get nasty integration questions like this, where you have to work out, you know, complicated looking areas, just don't worry about the actual integration part until you've set this up fully. And you'd be surprised how many marks this is worth. This is probably already sort of half the marks. And so if you are sort of rushing through and expecting that to be a tiny part of the question, then you're really setting yourself up to lose a lot of marks. So just remember that the setup is just as important as the integration part itself. Okay, then we're on to differential equations. And in the A level, differential equations are really just introduced at the last minute and not really touched on properly. So they're actually very simple because you only get one type, which is separable differential equations. And what I mean by that is, so far all we've done is said, okay, if we have something like dy dx equals some function of x, well, I can just integrate that on both sides. And the left-hand side, apparently, we think is y, and that's going to be the integral of f of x dx. But we can actually do a bit better than that. If we are given a differential equation in the form f of x g of y, then because differentials act like fractions, I can just do this. If I bring all the y's onto one side, the x's onto the other, that's fine, that's allowed. And then I just integrate both sides. Well, we've done the same thing to both sides, so that's allowed. And then we'll get a solution for y in terms of x. And so that's all that there is to differential equations at this level. And so the questions on them, while they're lots of marks, are usually relatively simple. So let's start taking a look at a few. And much like the connection rates of change in differential equations, the challenge here is often setting it up yourself, because I think the solving of the differential equations isn't too bad. So an area of neglected lawn is treated with weed killer. So we'll just call the area A. Before the treatment started, the area covered by the weed was 75 meters. So, okay, these are what we call initial conditions, and they're just bits of information they give you that allows you to sub them in at the very end of the question in order to find the constants of integration, so the plus c's and stuff like that. So it's worth writing them out, but it's just remember that these are never going to be used until the very end of the question. So at t equals 0, a equals 75, and t equals 2, 33.7. Okay, these are going to be just something we'll keep in our pocket for now. Let the area of the lawn covered with weed be A. Okay, well, we've done that. T days after it was treated. The rate at which the area covered by the weed is decreasing. Okay, so dA It's really just an exercise in translation. dA dt, that's the rate at which the area of the lawn is changing, is decreasing. So we know it's getting smaller, so it has to be minus. We need that minus sign. Don't forget that. If it's decreasing, it's minus. If it's increasing, it's plus. Is proportional to, so we can say equals to k, where k is a constant. The area still covered by the weed. Well, in other words, proportional to minus ka. Hopefully that should make sense. And just remember, with these kind of questions, they can be very intimidating at first, but honestly, more than 50% of the question is just in this setup. That's all you're trying to do. You're trying to translate the information. Okay, well, we've done that. And then it just says, basically, solve this. So now we've done this, all we need to do is get all the a's on one side, all the t's on the other, and solve. So let's do that. All the a's on one side, so that's 1 over a dA equals minus k dt. Okay, we integrate both sides. We get that ln a is equal to minus kt plus c. Now, just be aware, you only need one constant of integration, because I could put, a plus d over there, but then I could take that over and that becomes c minus d, which is still just a constant. So just remember, when you integrate, you only need a constant of integration on one side. Okay, and they want to find a in terms of t. Well, let's rearrange this for a then. We exponentiate both sides. We get e to the minus kt plus c, but that is just a equals e to the c times e to the minus kt. So the easiest way to write that is just say that e to the c is another constant, right? We can rewrite it as b, e to the minus kt. Okay, so we've got that. And then all we need to do is say, well, we have constants of integration in here that constants we don't know, b and k. How do we get rid of them? Well, we use our initial conditions that we wrote down earlier. So at t equals 0, a equals 75. So just subbing that in, we've got 75 equals b, because e to the minus 0 is 1. Okay, and we also have at t equals 2, a equals 33.7. So 33.7 equals 75 of e to the minus 2k. And so from that, I'm not going to bother doing it. We can find out k, and so our final answer will be sort of just a in terms of, well, it will just be something like a equals 75 e to the minus, I don't know, what is it? It's, let's just say I got, this isn't the answer, but let's just say I got the answer 0.6, and so then we're done. Okay, let's just do, let's do this question. Okay, water is pouring into a container at a constant rate of this. So what is that? Well, let's just say the V is the volume of water in the container. Well, they've already said to do that. And so it's pouring into a container. So in other words, the change in volume over time. So that must be plus 600 going in. And leaking from a hole at the base of the container at the rate, so leaking, e.g. going out, so we've also got minus 3V over 4. Okay. And so we've translated that, and then all we want to do is rearrange it to the form they want. So it looks to me like minus 4, multiply both sides by minus 4, we get minus 4 dv dt equals 3v minus 2,400, like they want. Okay. Initially, there were 200 centimeters cubed of water in the container. So what's that? That's an initial condition. So at t equals 0, v equals 200. We use that at the end. Now we want to find expression for v. So all we need to do is rearrange this to get all the v's on one side and everything else on the other. So looks to me like we can say that is 1 over, well, I'm actually going to divide through by 3 first, because I think that would be easier. So minus 4 over 3, v minus 800, just because it would be slightly simpler to work with. And so now rearranging that, we've got 1 over v minus 800 dv is equal to minus 3 over 4 dt. Integrating both sides, we've got ln v minus 800 is equal to minus 3 over 4 t plus c. rearranging that to get v as the subject. We get v is equal to treating e to the c as just a constant ae to the minus 3 over 4 t plus 800. Okay, and that looks reasonable. So now all we need to do is sub in this, our initial condition, and so we get 200 equals a plus 800, and so a is minus 600, and so that leads us to v equals 800 minus 600 e to the minus 3 over 4t, and that's their answer. State the maximum volume that the water in the container will ever attain. Well, these are nice last bits of the question, because you just sort of look at this and say, well, over time, what's happening? Well, this is tending towards 0, right? And so V max is just equal to 800, because once this term goes away, we've got 800 in there. Okay. Final part of integration, parametric integration. Now, this isn't the most difficult section, but it is something worth paying attention to and being careful, because I don't think it's given enough care by a lot of people. The main thing I want to say is that determining the limits in parametric integration is the bit that people don't pay enough attention to. And so just remember that in order to determine limits, you really need to know what's going on. So you need a graph, and the actual integration bit is not too hard at all. The integration of parametric integration, well, what is integration? Integration is always integral of y dx. And for parametrics, what do we have? Well, we have y is some function of t. Let's just say, so we've got y as a function of t and x as a function of t, for example. Well, so therefore, how do we integrate integral y dx? Well, that is just going to be the same as integral y as a function of t. And then we need, if y is a function of t, we need to be integrating across t, not across x. And so we're just going to apply the chain rule here to say that dx is the same as dx dt. And so this is what you want to actually integrate. In other words, you sub in your value of y, you differentiate your value of x, and sub that in, and then you just integrate. So let's see some examples. Okay, so let's have a look at some parametric integration examples. Pay particular attention to how we determine the limits, because those are the most important parts of these kind of questions. So figure above shows the curve C given parametrically by this. The curve meets the coordinate axes at the point P and at the origin O. Okay, the finite region R is bounded by C in the x-axis. Determine the area of R. So in order to do this, we need to know what values make this 0 and P. And so when is it meeting those points? Well, it's when y is equal to 0 for both of them. And so we can sub that in and say 0 is equal to 2 sine t. And so that means that sine t equals 0. And so that occurs at, well, for this question, it's nice and easy because it's at when t equals 0 or pi. And so actually, those are going to be our limits. Our integral between 0 and pi, remember it's integral y x dash dt. So it's going to be y, which is 2 sine t, times by x dash, which is going to be 3 plus cos t dt. And then, as you can see, this now isn't too bad for as far as integrals go. So it's not a particularly difficult question to finish. It's the integral of 6 sine t plus 2 sine t cos t. Okay, lots of ways we can do that. So we can say that that's equal to, well, sine t integrates into minus cos t, so it's going to be minus 6 cos t. 2 sine t cos t is sine 2t, so we can say that this is going to be minus sine, the integral of sine 2t is cos 2t, so minus cos 2t over 2. evaluated between these limits, pi and 0, and that will give us the area. Not particularly difficult, that question. Whereas this one, I think, will be more tricky. But the method is exactly the same. So find the y-coordinate of P. So P lies on C where x equals 3. We've got that x equals 3, which means that 3 must be equal to 6 cos t. And so it's when cos t is equal to a half, which occurs at t equals, I believe that's pi by 3. Okay. And so y is equal to 3 sine of 2 pi by 3, which is the sine 120, which is the same as sine 60. So I believe it's 3 lots of root 3 over 2. Okay. And so that's the y-coordinate of P. L, the line L is the normal to the curve at P. Okay, so what does that tell us? Normal to the curve at P. Well, that means L, which has equation y equals mx plus c, we know that at P, so at 3 root 3 over 2, we've got that the gradient of y is equal to, because it's the normal, minus 1 over the gradient of the curve evaluated at the point 3. But this is in parametrics, so we know that dy dx, how do we get that for parametrics? Well, that's just dy dt over dx dt, so minus 1 over dy dt over dx dt, but we're evaluating it at the point x equals 3, but in terms of t, that is at the point where t is pi by 3. So we need to know what the values of those are. So to do that, we need y dash, which is 6 cos 2t, and x dash, which is minus 6 sine t. At pi by 3, that's going to be 6 cos 2 pi by 3, so that's, I believe, minus half, so minus 3. And this is going to be 6 sine, so that's root 3 over 2. And so 6 of that is minus 3 root 3. Okay, and so finally we get the gradient m is minus 1 over minus 3 over minus 3 root 3, which finally gives us minus root 3, I believe, which if you look at the diagram, that looks about right for the gradient m. Okay, but it's also, we also know that the line goes through this point, and so we can say y, so we can say that 3 root 3 over 2 is equal to minus root 3, which is the gradient, times the x value, which is 3, plus c. And so I believe that gives us that c is equal to minus, no, it gives us c is equal to plus 9 root 3 over 2. Okay. And so then that finally gives us the equation of L to be y equals minus root 3 x plus 9 root 3 over 2, which you can see hopefully is exactly the form they've given if we rearrange it slightly. Okay, this normal meets the x-axis at q. So q, well, what is q? It's when y equals 0 on that line. So 0 is equal to minus root 3 x plus 9 root 3 over 2. And so we've got that x is equal to 9 over 2. Okay. And so then they want us to find effectively the shaded region. So let's just mark on everything we know. This is at the point 3, root 3 over 2. It's at point 3, and this is at the point 9 over 2. Okay, well, how do we get this area? Well, first of all, let's just check. So, okay, part C is just find the area, this whole bit, including that. So how do we find that area? Well, we need to know the limits we're integrating between. And we know that at this point P, we found that T, so at that point P, T is equal to pi by 3. But what about, how do we find the rest of this? Well, what's the other limit? Because we need to integrate between this point, when x equals 3, and this point. Well, what's that point? Well, that's when y equals 0, which we haven't done yet. And so y equals 0 implies that 3 sine 2t equals 0. And so sine 2t equals 0, implying that t is either equal to 0 or pi by 2. And so now we need to think about, well, which option are we choosing? Is it t 0 or pi by 2? And in order to determine that, it's not obvious at all. We know we want this point. And so what can we say distinguishes between this point and the other point where y equals 0 is that point? Well, we need to know which value of t we're using. So we need to check which one of those gives us a non-zero value of x. And so if we sub this back into x, we get x equals, well, for t equals 0, we get x equals 6. So that looks like it works, but so that's t equals 0. And for t equals pi by 2, we get x equals 0. Okay, and so what has that told us? Well, it's told us that actually this occurs at t equals 0. Now, hopefully that illustrates very clearly why you need to be so careful about figuring out the limits in these questions, because that is not obvious at all. It would be very easy to assume that that limit is when t equals pi by 2. But now that we've done that, it should be quite easy to find out this area, because all we're saying is, well, then it's the integral from 0, that's one of our limits, t, to pi by 3, the other limit, of y, which is 3 sine 2t, x dash, which is minus 6 sine t, and dt. And sort of messing around with that, we get that it is going to be, we've got a minus sign in, but that doesn't really matter because they've got, they want the area, so we can get rid of that minus sign, and so it can be equal to the integral, because as in the area can't be negative. So we've got the integral of 18 sine 2t sine t, or in other words, 36 sine squared t cos t dt. And then finally, the last bit, well, that should now be easy because you can see that we just do that integral and that will give us all of this. And so what do we want to do to get the shaded region? Well, we need to subtract this little triangle, for which we've got the height, 3 root 3 over 2. We've got the width, which is, I believe, what, 3 over 2. And so it should be relatively easy to finish off the question. Okay, and that's it for integration. So hopefully that was helpful. Quite a chunky topic, and so I recommend you sort of do the examples in this video that we haven't done and practice it yourself. But you can see that it's not too bad as long as you have a good understanding of all the ways of doing it. But the most difficult bit often is just knowing which method to choose. And so hopefully this video was helpful for that.